Let's now put this all together. You ready? Because here's the fun part for me. So waves. Waves is how light is interpreted. So guess what also is interpreted by waves? The colors that you see. And those colors, guys, are measured on a spectrum. It's called the visible light spectrum. Okay? It's part of something even bigger called the electromagnetic spectrum. And guess what? In the grand scheme of the entire electromagnetic spectrum, do you think our visible light portion is a large part of it or a small portion of it? Small. Oh my gosh, it is tiny. Because guys, our entire visible light spectrum is from 400 nanometers to 700 nanometers. Now, that chart over there, nano, big thing or small thing? Itty bitty little thing, right? Let's give you some colors on that. Ready? These are approximations. These are not locked in stone. But from 400 nanometers to 420 nanometers, the color that would be seen is violet. Purple. From 420 nanometers to 490 nanometers is blue. Alright guys, this is nanometers. Your eyes are so cool that they can interpret different shades of purple between 20 nanometers. To me, that's so cool. Hi.
What about people who are colorblind?
Okay, color blindness is something that is a genetic disorder, okay? So what happens is these people have difficulty interpreting these wavelengths of light. Okay? It's a genetic thing. So they have trouble. Usually people that are colorblind have issues where, you know, it's red-green. So they can see shades of red, shades of green, and they have trouble with certain things. Like, for example, my father-in-law can't see pink. Okay? And remember, does color blindness run more in males or females? Males. Because it is X-linked. A little bit of biology review for us. It's on film. All right, so 420 to 490. The next range that we have here is from 490 nanometers. Oh my god, I'm second guessing myself. Yeah, to 580. And this one's a great one. This one is green. Yay, go green. The next one is from 580 to 590. And that one is yellow. 590 to 650 is orange. And again, these are approximations. And from 650 to approximately 700, it's not exact, right around it, approximately 700 nanometers is red.
Why is yellow so small?
Yellow is just small. It's just a particular portion of our electromagnetic spectrum that has a small range. Because that's just how our eye is created and made.
Yellow's low.
Okay. Couple of things. We can't see above or below 400 nanometers, but up here, just to let you know, is where you find UV, ultraviolet radiation. Anybody know what comes after red? Infrared. Very good. I'm going to call that IR. Infrared is down here.
Action.
Action. All right. So now let's talk about frequency. Okay. Frequency. Frequency is defined as the number of waves passing a given point in a given amount of time. Let me say that again. Frequency is the number of waves passing a given point in a given amount of time. So let me draw you a couple of waves, and that's the best way I can think of to demonstrate frequency. I'm going to have letter A wave and letter B wave. Letter A wave. Be like this. Okay. And letter B. All right.
It's not right there.
Let's imagine for a second that when we look at letters A and B, this is the waves that pass a given point in 5 seconds. Make it up an arbitrary amount of time. 5 seconds. My question to you is this. Letter A or B? Which one has the higher frequency?
B.
B by a lot. Because, quite frankly, you get more what? You get more waves. There's a price to pay for that, though, isn't there? And that price is this. Which one has the longer wavelength? By a lot, doesn't it? If we looked at adjacent points on waves, let's just look at the crest. The crest of this wave, all the way to the crest of this wave, right? Versus the crest of this wave to the crest of that wave. Which one has a longer wavelength? Right? A does. Now, which one has the higher frequency? B. We get a lot more waves in a given amount of time, don't we? So, what I'd like you to point out, or what I want to teach right now about frequency and wavelength, is that if we looked at it from a proportionability standpoint, I don't even know if that's a word, okay? What type of proportional are they? One goes up, the other one goes
Inverse.
down. What do we call that? We call that?
Inverse.
They are inversely proportional. Can you have both? Can you get a higher frequency with a higher wavelength at the exact same time if you're comparing two waves? No. They are inverse to each other. All right. Now let's talk about the speed of light. Because we said, how is light getting to our eyes? How's it traveling? In what form?
Waves.
Waves. Those waves have a speed, don't they? And it's called the speed of light. Now, the speed of light is represented by a constant. And that constant has the letter of c, lowercase c. And what it is c equals, let's go 3 stiff fingers, 3.00 times 10 to the 8th. So is that a big number or a small number? Yeah, it's 300 million. So 3.00 times 10 to the 8th meters per second. So that thing is traveling 300 million meters per second. I need to do that fast. Because if you are, you should just sign up to play professional football for just about anybody. And, you know, chemistry will be nice to have in your lifetime, but, you know, go be Forrest Gump. Right? Just felt like running. So 3.00 times 10 to the 8th meters per second. Alright, so the last thing on our sheets is asks us to calculate frequencies and wavelengths. You've already told me they're what kind of proportional, class?
Inverse.
They are inversely proportional. Well, I'm about to give you an equation that demonstrates that relationship. And it is this. C equals a funky looking V. That stands for frequency. And this is going to be measured in a unit called hertz. Now be careful with that one, right? Hertz. That's H-E-R-T-Z. That's different from if your buddy comes up to you and offers you a Hertz donut. Okay? You don't want to eat that because he's going to hit you in the arm. Hertz donut. Alright? Anyway, so frequency times. Don't be hitting each other.
She didn't understand what it was.
She didn't understand Hertz donut? Nice. Alright, times this other thing, which is wavelength. Now, the unit on wavelength must be in meters. Here's why. Hertz is actually interpreted as waves per second.
Isn't that the
So
same?
Hertz equals waves per second.
That's the same shape as the fucking capacitor.
And wavelength is in meters.
The what?
Well, C was a constant that was 3.00 times 10 to the 8th what? Meters per second. Notice meters matches meters. Per second matches hertz. So your units have to match just like everything else in chemistry? Yes. This relationship, C equals frequency times wavelength, is inversely proportional. And as long as we have things in hertz and meters, we can then calculate them.